Okay, so we've got a couple more sections that we need to finish out session one, and this next one is probably the most important thing that y'all can actually remember when it comes to this course. What I'm going to tell you is what we're going to talk about from here on out. There's not going to be a day that goes by that we don't mention one of these three things, if not all three of them all the time. So this little section is what I call the big three: voltage, current, and resistance. So we need to know what voltage, current, and resistance are, because understand that what we're trying to do is we're trying to control the flow of the electron. Well, quite frankly, the flow of electron is called current. And so we're trying to control current. So we got to know what current is. We got to know how it's measured, what unit it's measured in, and we have to know a letter designation that goes along with it, because we're going to end up having a formula that we're going to use, and what we're going to be doing is having to recognize what number to put where in a formula. Well, the formula has the letters, the numbers have the units of measure, so you have to lock in on, first of all, what that variable is, what its unit of measure is, because that's what comes behind the number, and then what its letter designation is, because that's what's in the formula. So here we go. First one we're going to talk about is voltage, though. Okay, voltage is defined as the difference in electrical potential between 2 points. Let that sink in. Voltage is defined as the difference in electrical potential between 2 points. Now, we talked about ionization. We talked about like chemical reaction in a battery. It causes this ionization process, which is the losing and gaining of electrons. So the electrons that are forced off of one material are attracted and attached to another material. So that separation as a result of the chemical reaction actually creates, and you can think of it like a stretched rubber band. That rubber band just wants to reassume that shape. Those electrons just want to get back, but they can't get through the chemical that caused it to separate in the first place. But if I hook some wire around up to a light bulb and then back down to the other side of that battery, I can create from that electrical difference more electrons on one plate than there are on the other. That difference will now cause those electrons to flow through that conductor. We're going to make it do some work for us and flow through a light bulb and come back to that other side of that source where there was the absence of electrons. So they're simply coming back, just as a rubber band would assume its shape after you stretched it. So that difference is the result of that ionization. That ionization difference, as we call it, is referred to voltage. So voltage is defined as the difference in electrical potential between 2 points. The letter designation for voltage. And then the unit of measure for voltage So voltage is the difference in electrical potential between 2 points. The letter designation for voltage is V, or sometimes you'll see it referred to as E. In this course, we stick with V as the letter designation, but back in the day, it was used as E, and E was short for EMF. EMF stood for electromotive force, the force behind the motion of the electron, electromotive force. So that basically covers it, but you're going to need to know the definition, you need to know the letter designation, and you need to know the unit of measure. And as an example, I wanted to show you a letter designation is equal to the value and then the unit behind the number itself. So knowing the letter and the unit tells you what number to put where in the formula. That's why that's so important. Okay, make sure you get that copy. And just remember, folks, copy this stuff, because that means it's going in your eyeballs, and in order for it to get down to your hands, it's got to go through your brain at least one time. Like I said, I could give you all kinds of handouts and stuff on this, but copying it works. And then when you actually copy it, then it goes back into your eye again, and it compares, and trust me, this many exposures just by copying it is going to be helpful. And if you want to do studying, studying is not a passive event. You don't sit there like you're watching TV, like, no, it's an active event, which means in order to study, you have to be doing something. Either listening to a voice or watching a video or writing notes. That by far is the best way to keep stuff in your mind, is to write it until you don't have to look at it, to keep writing it. That way you know how much you've studied and that you've studied enough. It tells you that you know it. But if you just go look at the book, hey, I studied enough. Well, you didn't. So studying is actually an activity. So write this stuff down, help yourself out, get your money's worth. All right, next one we're going to talk about is current. Current is simply the flow of electrons, defined. So when those electrons start flowing, we're going to call that current. And current is what we're actually controlling. Now, there is something I have to tell you about the nature of electron flow. Understand that If I took a garden hose that was empty and I put a marble in, well, I put another marble in, put another marble in, put another marble in, put another marble in, and eventually that hose would fill up. And when I put a marble in, they would all shift over and one would drop out, right? So that's one way to think about it, wrong way. You see, my garden hose is already full. You got to think about it. We already said that everything in our world is matter. Matter is made up of elements and molecules. They're made up of atoms. Atoms made up of electrons, protons, and neutrons, and we're dealing with electrons. So does everything in our world have electrons in it? Yeah, it does. And the ones that are made for conducting only have one in that valence shell. And so we have a loaded garden hose, a marble hose, is just ready to have those electrons pushed by one. And as soon as it does, there's one instantly coming out the other end. That's why if you think about it, if you turn on the lamp, you're not waiting there a couple of seconds before the old electrons make it up to the light bulb. No, they're there ready to go, and they get shoved through there. So understand, if there is flow everywhere. If there's one path, if I've got one conductor, there is flow everywhere. Electron flow is like the movement of the individual links on a chain, on a motorcycle chain or a bicycle chain. You can't have one link moving without all the other links moving at the same speed, at the same time, same direction, everything. So think of electron flow like that. Once one gets moving, they're all moving everywhere instantly, okay? So that's the nature of electron flow. Marbles in a garden hose, push one in, one instantly falls out. You're not waiting to fill it up, right? All right, so current, the flow of electrons. The letter designation for current. So yeah, I didn't make this up. I think C was already taken for capacitance at the time by Mr. Faraday. So they went with I. I is chosen for intensity of flow. So current, the letter designation is I. The unit of measure for current is the ampere, or short as the amp. And the actual unit behind the number is simply an A. So that tells me if I see a number with A, I need to put that number where the I is in the formula. All right, so an ampere. What the heck is an ampere? Well, you got to understand we're measuring flow. Now, think about water flowing out of a garden hose. If I had the garden hose turned on, would I say, well, I got a gallon flowing out of this garden hose? Well, no, you wouldn't. You'd say I have a gallon per minute flowing out of this garden hose, or a gallon per hour. I mean, think about a gallon per hour. That's barely a drip. A gallon a minute, that's a pretty good gush. So it has to be with an amount, a quantity, over a period of time. So that's how we measure flow. Now, the amp is the unit of measure for flow, and it does incorporate a quantity and a period of time. Now, the quantity, now this is all in your book and everything. I just feel the need to tell you this. It's not important. I probably won't test you on this stuff here, but don't shut down. Understand what I'm fixing to say, because it's freaky deaky. So here's the deal. The quantity is called a coulomb. A coulomb, look it up in the book. A coulomb is a bucket full of electrons. Now, how many electrons are there in a coulomb? Well, there are 1.68 times 10 to the 18th power. Yeah, how much is that? Well, actually, next session, we're going to learn about exponents and why we use them and that sort of thing. But I'll tell you this, 1.68 times 10 to the 18th is that much. How much is that? Who can tell me how much that is? Well, what did I do? Did I put 18 zeros? No, I put 16 zeros, because that exponent is actually going to tell me how many times to move a decimal point. And it's telling me to move it 18. This gives me 1, 2, and then I got 16 zeros. So I move that decimal point 18 times. But how much is that? Well, let's see. All right. So there's hundreds, there's thousands, there's millions, there's billions, there's trillions, there's quadrillions, and then we have pentillions. So that's 1 pentillion, 680 quadrillion electrons moving. That's a bucket full of electrons moving. And how long does it take to get them electrons past one point? The amount of time, don't forget that amount of time. Well, the amount of time is not 1 hour. It's not 1 minute. 1 second. So we're talking about 1 pentillion, 680 quadrillion electrons moving past a single point in 1 second. And that's 1 amp of current flow. 1 amp of current flow. First safety rule, it takes less than a half an amp to kill you. Now, we're all going into industrial trades here, and the first thing we need to realize is we need to be safe. Now, electricity is not something to fear, but you darn well better respect it. Because the first moment you drop your guard, you're not thinking about something, you're thinking about the fight that you got in the wife or that guy that cut you off on the way to work, and you're not fully focused in on what you're doing. That's when accidents happen. So, folks, let me tell you something. Electricity is not something to fear, but it is something you darn well better respect. 1 amp current, that's a lot. So we don't deal with amps of current flow, not on the electronic side. That's electrical and power distribution and all that stuff. We deal on this side of the wall. We plug into a power supply. That power supply drops that down to a DC. And then we power up our electronics. Everything in electronics is powered by DC. We may actually distribute AC voltage, but then all of our electronics are powered by DC. And so our output currents are in the thousandths of an amp, or the millionths of an amp of current flow. So the amount of current that we're dealing with is negligible. The low voltages, think about batteries. How much voltage is there in a battery? In your cell phone battery, in your car battery. About the biggest battery I know is a double battery, and that's 24 volts because a car battery is 12. So we're dealing with fairly small voltage values, which ultimately we have small current flows. And if we're dealing with thousandths of an amp and millionths of an amp, we need to learn a little bit about exponents, and that's going to be the next session. So you definitely don't want to miss that one. That's when I'm explaining how to use the calculator, which, by the way, you need to make sure that you have a calculator for the next session. Now, I'm not a calculator salesman, and I'm not here to sell you a calculator, but I teach with the one that they sell out of the bookstore. It's the easiest one for people to get, and I teach button strokes. So you push this button and this button and this button. And so learning these scientific calculators can be a job, but we're going to get through it. So that TI-30X calculator, the one that they have, that's the one that I teach from. So the flow of electrons, the letter designation is I, and then the unit of measure is the amp, and you might see it written as the current I is equal to 2 amps. Unit of measure, letter designation. Okay? All right, get that. Don't really have to worry about the coulombs. All right, the last one we need to talk about is resistance. Okay, so the last of the big three is resistance. Resistance is defined as the opposition to the flow of current is offered by simple friction. It's the opposition offered by friction. So you think about it, a bunch of tanks going across the field, and all of a sudden they get to the tree line. Now they got to fight their way through the trees and roll over them. It's going to slow them down. So when there's no opposition, they flow freely, but if I have opposition, it will slow that flow down. So I've got this variable that is capable of slowing it down. It's like pushing on the brake of a car. It's going to slow the speed down. You increase the brake, the speed goes down. See? So you increase the opposition, the speed goes down. And resistance is exactly that. It's the opposition to current is offered by simple friction, just stuff being in the way those electrons have to fight their way through. The letter designation for resistance is R. That one's pretty easy, resistance R. And then the unit of measure is called the ohm. They use the omega symbol to represent the ohm. And you would probably see it written something like this. That the resistance is equal to 200 ohms. So the unit of measure tells me where to put the number in the formula because of the letter designation. All right? So those are the big three. Now, you got to understand this whole concept is about controlling current, controlling electron flow. Now, we know there's two forces that we're going to use along to help control that current flow. One of them is voltage. That's the difference in potential. That's how much I'm pushing on the electron to go back. That's how far I've stretched that rubber band. That's the difference in electrical potential. So that voltage, that's going to make those electrons move. But then I got this other variable called resistance that's going to slow it down. It's kind of like controlling the speed of your car with the accelerator and the brake. If I increase the accelerator, will I increase the speed? If I increase the brake, will I decrease the speed? So I've got these two relationships to help me control current. So understand, we're going to hear current, voltage, and resistance every day from here on out. So the sooner you consume this, the better off you're going to be. We've got one more little section here, and then we'll do that in another short video, and then that'll be it for session 1. Thanks, folks.